Okay, so I want to take a look back at these ionization energies that we were going through before. So before we looked at them with a simple lens, like it was like using the Bohr model, and we just said, okay, if this is aluminum's ionization energy, you saw this table, no graph. Oh, there's a jump after the third one. And, going back to what does aluminum look like in a Bohr model? Let me pull that up. Okay, here it is. Here's the Bohr model for aluminum. And when we go back and look and see, hey, there's 3 electrons in that outer ring circling around here. So what's kind of going on? Let's go back to the screen. And, oh yeah, there's a jump between that because I was removing these first 3 electrons. And now I'm removing the 4th one from the next ring in. That's closer in. Coulomb's law, when things are closer and they're attracted, it's harder to rip them apart. So after I remove the first one, okay, I took from the outer ring. I removed the second one from the outer ring. I removed the third one from the outer ring. And those were just kind of normal. Why did I see a big jump? Because when I removed the 4th one, now it's got to come out of this second ring. And that's kind of what we use to explain that. And that's using an incorrect model. It's not 100% wrong. It's not bad. It's a different energy level, would be the correct term there. That's why we would see a jump. So instead what I did was I just plotted these in Excel. And so you can see I made a graph. I actually put a 0, 0 there, meaning if we don't ionize, it doesn't take any energy to remove an electron when you don't do anything. So I put a 0, 0 point. So jumping from the 0 to 1 point, we had a difference of about 600. Now, I don't know if you can see this real well, but there is a little increased slope here on the graph. It's kind of between 1 and 2. It's kind of hard to see based on because it's so steep on the right side of the graph. But there's a slope. It increases. If you look real close, you can see it kind of increases in slope, and then it decreases in slope between 2 and 3. So now we can use our actual model of atoms to try to explain this. We got a difference here of around 600, 0 to 600, okay, roughly. Then there's a small jump. Now I increased it by about 1,200. Here, it's not quite 1,200 here. And then, of course, we see a bigger jump. So why is there actually that little jump here? It's obviously not as big as going from 3 to 4, the 3rd ionization to the 4th ionization, because there we're looking at around 10,000-ish, 9,000-ish sort of a jump. Well, what's happening is you're moving from different sublevels. So if I'm going to draw what aluminum looks like, just the very top of it, I'm not going to draw the whole thing, but here we go. We'll start with, here's the 2 and the 3s. And here's our 3p, and aluminum has the 1 and the 3p. Actually, you know what? I guess right down below it, I'll draw the 2p, and of course it's got that full. Okay, so if I'm looking at the first one that I'm going to remove is actually from the 3p sublevel. So let me see if I can't just get rid of that, or if I just tap it. Oh, there we go. Well, that sublevel still stays there. Okay, so that's the first one. That's going to be gone, and so I see a certain energy. The reason I'm getting a small jump between the first and the second one is I'm still in the 3rd energy level, but I'm removing it from a different sublevel. An S sublevel is closer to the nucleus. Not by a lot, but it is closer, and therefore it's going to create a little jump here. So, okay, so in order to take out the second electron, so in order to go from the first ionization to the second one, what I now have to do is I now have to take out this electron here. And I'm just going to erase that. So now I'm down to 1. Well, I took 1 out of the S level, okay, the next one's out of the S level as well, so I kind of bend back down again because I don't see that big jump. So once I've done 3 ionizations, that also comes out of the 3s sublevel. And now if I want to take the 4th ionization, I got to remove from the 2p. I see a huge jump in energy to remove something out of this 2p level like that. And now I don't see as big of a jump because I'm already removed from the 2p. So I got to remove another one from the 2p. And you can imagine I would see this for a while until these are all gone. Until then I have to remove from the 2s and it would increase. Just to show you maybe another example of that, here's calcium. Same kind of idea. I will draw what calcium looks like. So we've got the 4s has 2 electrons. And then 3p is full. Oh, we got a mistake on this slide here, but I'll correct that here in a second by writing over it. And then after that, it would be the 3s. Okay, so there it is. I'll fix it for the one I upload. I'll correct it. But on my screen, it says it has something wrong. I have to change. Anyway, I'll change it in a second. So the idea here is here's calcium. Well, I got a couple problems with the calcium ones. Wow, I got to fix them. Okay, so those remove symbols are wrong. I'll try to fix them for the slides that you get. But maybe, hey, let's see if you can spot the problem. Something on the graph that's labeled. Okay, so the first thing that ends up happening here is, I don't see a big jump. I remove around 600, and then I remove about 600 more-ish. So there's really not a jump there with 1 and 2, and you see like a straight line between that. When I'm not actually removing from the 3s, like it says down below, I'm actually removing from the 4s. Okay, and I'll take those out. So after calcium has undergone 2 ionizations, those 2 are gone. We're moving from the 4s. Okay, now if I want to remove the third one, I have a jump because now I'm removing not from the 2p like it says on this graph, but actually from the 3p is where we're removing those ones from. Okay, so I can remove that one. And these are actually from the 3p as well. So as I'm removing them, I'm constantly removing from the 3p. So when I switch sublevels from 4s down to 3p, that's when you see the big jump. And then we're not seeing the huge jumps again, removing from the other 3p orbitals. So this one also should say remove from 3p's here. And I'm not showing on there when we're removing from the other 3s's. All right, so I got that one now fixed. I'll have to fix those in the slides that you guys have. Okay, so here you go. What I'd like you to do is I'd like you to pause the video here and try to figure out if you can explain. So can you explain to me in words, why are we seeing the jumps that we're seeing? Okay, I don't have them graphed right now. I'll show you that later. But see if you can explain what's happening here, where the jumps occur for silicon. And then good luck without looking ahead. Can you explain it for gallium, an element that's further down? Okay, I'm going to go through and give you the answers. First for silicon. Let's make sure that I have the correct orbitals there. Looks like I do labeled, so I didn't make a mistake on this one. But why are we seeing the jumps there? So here you go. Silicon, if we were to draw it, it has 2 electrons in the 3p. 1, 2, it looks like that. And it also has 2 electrons in the 3s. And then 1, 2, 3, it has the 2p's full. So I can draw that. And so when you're removing it, the first little jump that you might notice is between the second and third ionization. We were going up about 700-800 here, from 0 to that, and then this to here, it's about 700-800. But now we have a jump of about 1,500-1,600. Okay, it's small compared to the big jump, but it's there nonetheless. You can kind of see it on the graph there. So what's happening? We saw a small jump between the second and third because we were removing from the 3p. Now we are removing from the 3s. That's how you would answer that. Why are we seeing a jump between the 4th and the 5th ionization? Because we were removing from the 3s, and now we are removing down an energy level into the 2p. So that would be your answer for silicon. Gallium's a little bit trickier to answer, and I have these labeled correctly, so I did not make a mistake on labeling the graph this time. If we are drawing gallium, this is what it would look like. So gallium has the 4p's. It has 1 electron in it. And then it's got, the 3Ds are full. And the 4s's, now I'm drawing it this way for a certain reason. If some people saw it, they might gripe about me having the 4s right now below the 3D. But anyway, this is how you maybe have drawn it when it started to fill up. And so what ends up happening is with the first ionization, you see 1 remove there from the 4p. Okay, so then that's gone. That you probably did okay. But even though the 4s fills up first, once these are full, they can switch how much energy they have. The 4s and 3d are actually really close in energy. And so we always remove from the 4s before we take from the 3d. I know the filling up order doesn't work that way. It fills up 4s before 3D, but when we remove, we also remove from the 4s first. So that's why, okay, why is there a jump between between 1 and 2? Well, because I was removing from the 4p, now I'm removing from the 4s. Then I remove 2 of those, and so I'll remove my 4s electrons. There's my second ionization. There's my third ionization. And we're going to see a jump between the third ionization and the fourth, because now we are removing from the 3d in order to do that. We were removing from the 4s, we're jumping down an energy level into the 3d. And I know it's a little bit backwards and a little confusing, but you remove from the 4s's before you remove from the 3ds. So I just want to show that again here. The order of removing is not the same as the order that you add electrons when you're sort of setting up those electron configurations. When you remove the electron orders, okay, 4p's would be removed first. Then we'd remove 4s's. Then we remove 3ds. Then 3p's, etc. Okay, we can think of what comes after the 3p. Well, then it would be the 3s, and then the 2p's, and so on. Okay, so watch out for that. That is your ionization energies revisited.